Hi, in this video we will learn what is the steady state of a Markov chain. Well, first recall that every Markov chain has a transition matrix, yes. So we denote it by P, and we usually fix an initial state vector, which is a vector we denote by x naught. And then the other steps, or the state vectors in the other steps, will be given by this fact that state vector at k plus 1, the next step is equal to p times x k. Very nice. And this way you will see that if you repeat, you start with x0, x2, x1, and then x2. If you continue this process enough, you will reach to a vector. Let me write as x. Well, when you apply p to it, it will stay x again. So it will stay fixed. When your state vector gets to that point, you're not going to move. It will be steady at that point. So this is the definition. State vector is x is called the steady state if when you multiply x by p, you get x back. Okay. And while there are two facts here, remark one, that every Markov chain has a steady state. Every Markov chain has a steady state. While actually a non-zero steady state. Zero is always satisfying that equality. P times 0 is going to be 0 vector, but non-zero steady state. And when you see that, while you're basically trying to solve this equation, usually when we're trying to solve equations, we have one x in it. So we can do this by 1 minus, sorry, let me write it this way, ix minus px equals to 0, and then you factor x, I minus p times x. So steady state is a solution for a system of linear equation with the augmented matrix I minus P 0. So you solve it, you find a solution. So this satisfies, well, this remark that I'm saying, it's saying that it's always going to have non-zero solution. And when it comes to non-zero solution, you know that this is trivial homogeneous system, and non-zero solution, it means that it will have infinitely many solutions. So non-trivial solutions of I minus P0, if exist, will be infinitely many. So infinitely many non-trivial. Which one you want us to fix a steady state after solving the system, after solving the system this, we make sure that the sum of the entries or components of the solution is equal to the sum of the components of the initial state vector. So this way you basically fix it to be the steady state. Okay, so let's see some examples here. So find the steady state of Markov chain with the transition matrix this and initial state that. So transition matrix is given. We have to solve I minus P0. So in this case, it will be 1 minus 0.2 minus 0.7 minus 0.8, 1 minus 0.3. This is 0, 0. Well, this guy is 0.8, negative 0.7, 0.7, and negative 0.8. Then we try to solve this. Yes, we can do R2 plus R1. This way we will get 0, 0, 0, 0.8, negative 0.7, 0. And then you see that this guy is going to be a free variable. So x2 is going to be free variable, and 0.8 x1 minus 0.7 x2 is equal to 0. From this, the solution for this guy is going to be 7 over 8 t and second component t. Well, t is a free parameter or variable. Now, how are we going to fix it? You see, the sum of the components of the solution must be equal to sum of the components of the initial state vector. In this case, we will have 15 over 8t equals to 15, and from there t is equal to 8. Then the steady state is 8 times 7 over 8. This will give us 7 and 8. This together is the steady state of the Markov chain. Let's do another example here. So here we have find the probability vector, which is steady state of the Markov chain with the transition. Well, we know what to do with the transition. We do 1 minus solve this. But what does probability vector mean? Probability vector means that the sum of the components of that vector must be equal to 1. So let's solve this and see what does this give us. 1, negative 1 over 3, negative 1 over 3, 1, negative 1 over 2, 1, negative 2 over 3, negative 1 over 2, negative 2 over 3, and 1. Oh, this is augmented by 0, 0, 0. this is a system we have to solve it, yes. To just make our life easier, what we do, multiply row 1 by -3, row 2 by, actually let's just solve this one, yes. We don't need to do more works. I will leave the solution of this guy for you. I'll just write the row echelon form of this matrix: 1 0 0 0 1 0 -2/3 and -1 0. This way, when you look at this guy, what you notice is that, well, this guy is going to be a free variable. So x1 is going to be x3 is going to be free variable. X2 is going to be the same, or x2 equal to x3, and x1 is going to be -2/3 of that free variable. Plus, it goes to the other side. Now, this is the solution for 1 identity minus p and 0. And what we need to check at the end is that we want probability vector. Means that when you add the components, we get 1. Here you have 6/8/3, t is equal to 1. That means that t is 3/8. So the steady state is going to be 2/8, which is 1/4, 3/8, and 3/8. So we first find one identity minus p and 0, and then make sure that the sum of the components have the condition we want. So this is steady state of a Markov chain.